That's exactly, this will take another lecture. Today we'll only start. But that's the only thing what remained, basic problem. To describe dynamics, we have seen we have to define the field, how the field acts on the object. We've seen it is an antisymmetric tensor, but how this tensor is defined, how we'll find it. So we have to have a new model, and we'll see that we'll have to have a lot of changes. For instance, that the Cartesian coordinates that we use till now, and it's mostly used, are not so exact fitting for the problem. So today's lecture will start the whole outline, how you have to describe fields propagating with speed of light, which are all the fields that we know. Most of the talk is from the paper appeared at the end of the last, in 2019, together with, God willing, one of my students and Swiss Carl. The paper is called Prepotential of a Field Propagating with the Speed of Light, and it's dual symmetry. It was in the first message that I sent you. You have a reference, it's free open access. Shortcoming of the description of the electromagnetic field by using differential equation. Basically, mainly also the Cartesian coordinate. Classical physics uses differential equation in variable time, t, to describe evolution. What does it mean to use a differential equation? Differential equation expresses the state of the physical system at time t plus delta t, or small value delta t, if you know its state at time t. The acceleration of an object, that's what is defined by Newton's law, depends on both the state of the moving object, mostly the position, and the state of the sources of the field affecting its motion. So in order to describe the motion of the object, you have to know also where the sources of the field were positioned. The sources of the object are in general positioned at different places. We are talking action at distance. When the action is not at distance, you don't need modern physics. Newton's laws are perfect. No correction needed. Where is needed the corrections? The corrections are needed when the object that is affecting you is positioned far away, a different position. And the assumption that the acceleration there in Newtonian approaches at the time t depends on the state of sources at the same time. What does it mean? That the source affects you immediately, equivalent to the assumption that the field acts instantaneously, which is assumed in classical physics. Thus, this assumption is valid only in classical physics, and we know it is wrong. There's no instantaneous effect of field. Thus, the description using differential equation involving the states of the source and the object is restricted to classical physics only. So we have to have somehow a way to change things, to find something more fitted for relativity. Use of fields to describe action at a distance. To solve this problem, we use the following. We know from relativity that all fields propagate with the speed of light and not instantaneously. This may be followed from the fact that fields propagate by use of particles of mass zero. And as you have seen, to be mass zero, you must move with the speed of light. Otherwise, you have no energy and no momentum, you don't exist. So since they are the carriers of the field, so the fields move with the speed of light. So the only way to get around, maybe that's the way that's used now, how to get around. We solve first the equations or the description, we find the description of the field generated by the sources. And if we know the field at any space-time point, we now can describe the motion of the moving object based on the field at the same point. It means we don't look first of all only on the sources alone. We find how the field looks at the given point. When we know the field there, then we know the acceleration. And in this way, we already took an account that the propagation of the field. We don't look where the source is at the time t. We look what happened with the field at the time t at the given point. So that's very basic idea to introducing field. It was introduced before relativity, already in electrodynamics. Maxwell equations, the equation for the field, because they saw that in electrodynamics we cannot use direct interactions, and it was not understood that time that the reason is because the field propagates the speed of light, and that was the reason why the Lorentz transformation came alive. It was the transformation that fit the equation, the Maxwell equation. So to describe the field at time t, we have to know the state of its sources at earlier time. What time? Exactly the time that it took for the field to reach our point at time t. Now, the problem is not solved in general. And there's still a lot of work to done to solve it in general. Because really, what we know now only with the following assumption. We know how to find the effect of the field from the sources if we assume that the motion of the object, its effect on the sources is negligible. That means we assume the dynamics of the moving object does not affect the source. For instance, we cannot use this method if we have a binary star, because each one affects the other. So there's no source and object. You cannot say that the motion of the object will not affect the source. So there's no model at this time at all how to get to this problem. But I think the way as we will treat the first problem effectively, maybe it will help us. We have a half a way toward the general problem. So we will describe a field propagating with the speed of light from information about its sources. Assumption is we know what happened with the sources, and we will describe the field propagating with the speed of light. Now, since we may assume that if we have several sources, the effect of them will be some kind additive, then you have to be careful. You cannot add the acceleration, but some kind we'll have to be more careful where we can assume it to be additive. So it's enough to start the problem to solve for single source. And that's what we'll try to move forward today. So a field generated by a single source. So we start the following. You want to describe the field at some space-time point P at this point. And the field is generated by source, which has the walled line L. So we assumed in this setup that we know what happened with the source at different times. Then we have to define the retarded position Q, which is the intersection of the past light cone with vertex at P. We build up a light cone, and we look the intersection of this cone with the line L. That means this is such point that the position of the source, when he was at that point, the field of this source, when he was here, reached me at the time t. So this is the only relevant information for me. It doesn't matter where he was here, it doesn't matter where I was here. For instance, if I observe a star which is 1,000 years far away from me, light years from me, what happens now is totally not relevant to me because the information about what happens now will reach me only 1,000 years later. So really the understanding as in Cartesian coordinate what is now doesn't make sense in relativity. What we observe is the only things which are on the backward light cone. Only those events send us effect. They are affecting us. They send us light signals, they can send gravitational waves, everything, information that we are getting about the world is only a three-dimensional, because the light cone is three-dimensional, is everything on the light cone. Within the time, the light cone moves upward, but at each time, we have only events on this light cone. And all the dynamics has to relate with events that happen on this light cone. All other events are not relevant. Either they will reach me later, either they were in the past. So what is relevant, what is now? And now is not simultaneous event at the same time. The event that the propagating with the speed of light reach the information to me now. And assuming that the field propagates at the speed of light, the field at P depends only on the state of the source at Q. We will see it's not only the position, it may depend on its velocity and even on its acceleration. But all those things are things which are at the same point Q, not important at other points. What we will play the main role that will be able to do analysis is using that the vector PQ, since it's on the light cone, is a future pointing null vector. It shows you the direction of propagation of the field that reached me now. This is a system I introduced a few years ago. I call it bipolar coordinate system. I have not checked, maybe somebody else had it earlier. It's worthwhile to check out the literature, but at least it was not used. It is used on the fact that 4 equals 2 plus 2. We have the dimensions of the Minkowski space is 4, and you want to split it into 2 subspaces of dimension 2. One, the first one, let's call it M1. The basis vectors are denoted E0, E1, E2, E3. Now we pick up a regular plane, as we like always to work in classical, the XY plane, that's M1. And we'll take the time coordinate E0, add to it one spatial coordinate. So this representation really needs to break a little bit the symmetry to pick up a preferred direction in space. It is based on, otherwise you cannot split it, and all those nice results that you obtain need this splitting. For us, usually the Z direction is the preferred one because the direction that we feel the force, the gravitational force in our lab, so that's the preferred direction. And we introduce bipolar coordinates, which will have 2 coordinates of length, unit length, and 2 angles. For any vector R in M, and here they are defined. Really what they mean as follows. You took, in M1, XY plane, or R1, R2, you use regular polar coordinate that we are used to. Rho1 cos sinus phi, rho1 sin phi, rho1 is larger or equal to 0, phi is from 0 to 2 pi. In the plane M0, we use hyperbolic coordinate, where we use the same thing, cos theta and sinh theta. You saw those things when we have, for instance, Lorentz transformation. Those are the elements of the time vectors. What is interesting with these coordinates, you get a very simple formula for the Minkowski metric. Minkowski metric is rho 0 square minus rho 1 square. Because if you take you have the square of this minus all those things. Square of cos minus sinh is 1. So you get rho square, and cos square plus sine square is 1. So you get minus rho 1 square. Very simple formula. What is even more nicer, the light cone. The light cone will not have now a singularity at the vertex. It will be a hyperplane. Rho 0 equals rho 1. That's when the norm is 0. And any null vector will be of the following form. A null vector r squared equals 0. Then rho 1 is equal to rho. We call it rho, and we have this expression. These are the coordinates that are used in observational in astronomy. It's not abstract coordinates. Those coordinates are really easy to observe. The coordinates t and using simultaneity, it's almost impossible to observe. But these coordinates are the ones that we observe. Let's think why. An astronomical observation contains the following information. It has the time when I observed it, and two angles defining the direction from where I saw the star. That's the direction and some information about the distance. I'll explain you how they get it. This is the most difficult part, but we will see that in our description, this almost disappears, the distance. We'll need basically the angles, which are the best measured. The easiest way is to measure angles. You look on a star, you look the direction of your telescope, and you have the two angles. Mostly, we are used to have the two angles in spherical coordinates. Even in spherical coordinates, the angles were measured by theta tilde and phi tilde. Then the theta is a simpler function of theta tilde. You have to take cosine of theta tilde and tangent hyperbolic inverse. This will give you the theta, and phi tilde is the same as phi. That means you have an easy way to calculate the two parameters of our coordinates, theta and phi, the two angles. And the time is the time that you observe. So you don't have to think about the event. How to find the distance? This is a little bit tricky, but we are lucky there is a way how to find it. There are some way to find it by using what's called trigonometric parallax, but that works only for nearby stars, which are not far away. And I'll show you how. And the other one are built up on observing some stars, Cepheid stars, which are types of stars which have that pulsate radially, varying both in diameter, temperature, well-defined stable period. You have some stars that are not permanent, they are pulsating. The pulsation is easy to observe, and you can observe exactly the period of them. And then it was found that the intrinsic brightness is a function of the period. So let's explain a little bit with the pictures. Here's how it works with the parallax. With the parallax, you have a star that you want to observe, and you have to measure its position on the sky at 2 points, which are far away by a half a year. So, for instance, in December and in the summer. Everything in astronomy is measured with respect to the map of far removed stars. This map is like static. And we see where we have seen the star in December and a half year later. So with this, we can understand what this angle is, and using trigonometry and the distance of the radial distance of our trajectory, we can figure out the distance. But the angle became very, very small as the star gets further away, and therefore we can only use it for stars which are not far away. So how we know the distances of galaxies? You have millions years, light years, how we measure them. So we were lucky that in the sky there are those types of stars, the Cepheid variable stars. And for them, for the stars that are close to us, that means nearby stars, we were able to find the connection between the period and the intrinsic brightness of the star. There's intrinsic brightness and observed brightness. When a star is, as further you are, the brightness goes down by r squared. So if you know that the star had a brightness at such distance of this type, and it's twice as much, you will have the brightness 1/4. So if you see the same star, you know the observed brightness, apparent brightness, and if you know the intrinsic brightness, you have done. All those stars, the intrinsic brightness is a function of the period. And it's the same function for a lot of stars in the nearby region, where we're able, by using trigonometric parallax, to define the distance. So now when we look at a new galaxy, we are looking, and all galaxies, the nature put there a few such stars. For those stars, we are able to measure the distance, and we assume the galaxy has the same distance as those stars inside. So that's an interesting way how people in astronomy measure the distance. So there's a way really to get all the variables needed to get our polar coordinates. So this coordinate system is really easy to connect to the real observation. By the way, the current setup of GR, to get something that even know all the equations and all the metrics, etc., to get connected what you observe really is very, very complicated. And therefore, I think moving to a coordinate system which is connected with the real observation will help us better understand a lot of things. Now, with these coordinates, I want to introduce a local basis. All the calculations will make it much easier if you work in this local basis. That's only the last 2 years I introduced them, because this really made a big difference. I would not be able to teach you this material 2 years ago. Even I had the formulas. Each formula was a disaster how to get to it. Calculations of a few pages. Now everything is directly observed. So what is the local basis? If you have a coordinate system, you take the partial derivatives of the position vector with respect to each coordinate. Here how it looks like. The local bipolar basis is the following way. The first vector is you differentiate the R, which had all those components, by rho 0, coordinate number 1. And you'll get cos and sinh, because the coordinate gives you rho 0 cos, and here we have rho 0 sinh. And the middle term didn't have rho 0, so they are 0. When you differentiate by rho 1, you get the middle term, and you get cosine and sine. Now you have two more variables, the angles. When you differentiate by the angle phi, we call it d2, you get sine and cosine, but you have to turn it into the right unit. They'll have rho 1 in front of them. To normalize, you have to divide by rho 1, and it's done always in polar coordinates. You know that the line element is rho 1 dt, which is the arc length. The same thing you do with the d3, differentiate by theta and divide by rho 3. you got an orthonormal basis. The norm of D0 is 1. Cos square minus sin square is 1. The norm of this is cos square plus sin square is 1, but on the spatial coordinates, it's minus 1. The same thing here is minus 1, and sin square minus cos square is also minus 1. They are orthogonal, and inner products, since this and this different coordinates, they're 0. Those are also orthogonal. All of them are orthonormal bases. Very nice bases. Work with them is the same as the natural basis in Minkowski space. By the way, it depends only on what? Only on the angles. It's independent on the coordinates of distance. And not on a base depending on the angles. Also, another interesting properties. If you differentiate these bases by the variables, by the angles, one basic element goes to another. If you differentiate D0, you get, instead of cos, you get sinh. Instead of sinh, you get cos. It's exactly D3. And the same thing, differentiate D2, D3. Has to be D3 by theta gives you D0. D1 by phi gives you D2. And D2 by phi gives you negative D1. Okay. How looks a null vector? A null vector looks in this using this basis is the sum of the two vector bases D0 and D1. Now, next thing I want to find a representation of the Lorentz group that will keep this information preserved, having some invariance for those coordinates. Really, we'll find a Lorentz transformation that keeps the two angles invariant. Looks a totally miraculous thing. We want to have both rotations and boosts, and the angles will still remain the same. That's what we are going to show. But for this, we'll have to introduce a few more notations. So we have to have now, we want to have a matrix representation of space-time. This is only not changing the space-time, only to have a more convenient way to use it in order to allow us matrix multiplication. So we use now that 4 equals 2 times 2. Instead of having a vector of length 4, we'll make from it a matrix 2 by 2. And you'll see the matrix will be complex, and here the complexification of all our model will come in. Without this complexification, it's impossible to do those things. And to understand till the end, the complexification is still a problem to do. What happened with the presentation? It got stuck. Ah, here it is. So take any vector x in M. We represent it as 2 by 2 self-adjoint complex valued matrix. How the matrix is complex self-adjoint? On the diagonal, they are real. Off the diagonal are complex adjoint. So you have off the diagonal, you put there x1 and x2 plus ix2 and x1 minus ix2. And on the diagonal, you put, and the 0, 0 place is x0 plus x3, and the 1, 1 place is x0 minus x3. What is nice with this representation, that the interval is simply the determinant. Determinant of this matrix is x0 square minus x3 square minus x1 square minus x2 square. Exactly the interval. This is very convenient. Why? Because Now, if you multiply by any matrix of determinant 1, it will preserve the interval. So you have a very large collection of mappings transforming the Minkowski space in preserving the metric. Now, to work with them, you have to, it's easier by using Pauli matrices. The Pauli matrices are the matrices near each coefficient. For instance, the near x naught is the matrix 1, 1. That's sigma naught. Near x1 is the matrix 1 and 1 here. And near x2 is this matrix, and near x3 is 1 minus 1. So those are, turns out those matrices were introduced by Pauli in quantum mechanics. And so we can express those through those matrices. What is the importance of those matrices? They are very nice multiplication rules. Okay, sigma 0 is 1, so if you multiply everything by sigma 0, it's the same, you get sigma j. But when you multiply sigma 1 by sigma 2, you'll get minus I sigma 3, and do cyclic permutation, and then you get sigma 2 sigma 3 equals minus I sigma 1 and sigma 3 sigma 1. It's a cyclic permutation of the same again. But even more important is canonical anti-commutation relation, which tells you that you take not the commutator, anti-commutator. It means product sigma I, sigma j, sigma k, and sigma k, sigma j. You'll get 0 if j differs from k. That means if you take a square or some power, you get only diagonal elements. And that's very important property. And this basically physicists were looking for such matrices having this anti-commutation relation to simplify certain things that you want to do. Now, what we'll be able to get, Lorentz group representation, new one, not the regular one that we had the last time, a new representation. How it comes about, if we look, the Lorentz group acts by boost and rotation. So if we want to represent them, boost and rotation, both we use the representation of their generators. The regular representation is denoted by pi of the Lorentz group. It will act on these matrices as it has to act on matrices. Those are matrices rank 2 tensors, and we had a way how the tensor transformation from one basis to a basis. For matrices, it is equivalent to multiplication both right and left. And the matrices, those will have determinant 1, so it will preserve it will be the Lorentz group representation. But now, we can represent only from one side multiplication. We mustn't use as transformation of matrices. We have two different representations, one multiplication from left and the other one multiplication by right. We have to pick up one of them. We picked up at this time the left because we are mostly used acting on something on a vector from the right. So we use the left multiplication. So how we do it? We take the matrix representation of the vector x, multiply it by the Pauli matrix if we want to have a boost in direction j. Now we need to add a half. We'll see in a minute later why. Without the half, it doesn't work. And then move backward to get a vector. What is surprising that for rotation, the only thing is you have to change the coefficient instead of half by I over 2. When I got the first time, I was surprised. How can it be? Those are two different actions. boost and rotation, and how we got them only multiplying by I. But we have to remember that the Lie algebra is a real Lie algebra. And the vectors, a vector in I time, the vector are independent over the real space. They are dependent in as a complex space, but on the real space, they're independent. So really, those things, this definition gives you the right representation of the boost and rotation, and I will show how to get it. It's very straightforward to check it. The commutation relation follow only from the multiplication rules of the sigmas. Because what we have to check, we have to multiply representation of the two boosts and then change the direction of the multiplication, the commutator, and get the right commutator. I'll show you how to do the commutation relations of representation pi L. I have to tell you first what are the commutation relations for the generators of boosts in the Lorentz group. So if you take two boosts, Bj and Bk, then the commutator will be a rotation matrix with the index, the missing index. And the sign depends on the epsilon, Levi-Civita antisymmetric index, and that's the formula. So if you take, for instance, B1 and B2, you'll get rotation about the axis Z, which is in the same rotation in the plane 1 and 2, x and y, and with the sign minus. If you take two generators of rotations, what you get, rotation is a group. As we had in the bounded symmetric domain, the linear part is a subgroup. So they will give, the commutator of two rotations will give the rotation, also with the missing index. And if you take a boost and rotation, you'll get a boost. So if you change the direction, you'll get also with a minus. So they are very similar formulas. And using that, the boosts are not a subgroup, the rotation is a subgroup, and the boosts act on it as in any bounded symmetric domain. So I want to show you how you prove this for j equals 1 and k equals 2. So what we have done, we have to take the B1. B1, as you have seen today in Scar's lecture, is E0, 1, 0 rows and the 1 column, plus E1, 0. B2 is E0, 2, plus E2, 0. Now how we multiply them? When you multiply in this direction, so you need that the column, that means the lower index, will coincide with the upper index. So 1 you don't have here, you have only a 0. So they got contracted and you get 1 and 2. 1 above and 2 below. If you multiply in the other direction, so you have to look for the columns to be equal to the row. You don't have a 2 here, but you have a 0, and this corresponds to 2 and above and 1 below. So tensor notation really makes the calculation very straightforward. So you know that the commutator between them is B1, B2, is this minus this, is E21, E12, and E21, negative, which is the rotation matrix about the z direction, and with a minus, because there you had to have 2, 1 minus the opposite. Now let's check that under representation pi L, we have the same identity. So we write down, first of all, the product of them under pi L. So here it is written for B2. It is phi of x half of sigma 2, phi minus 1. Then I have to apply phi of it and multiply by half of sigma 1 and phi minus 1. Now phi and phi minus 1 cancel out. A half and a half gives you a quarter. All the maps are linear. So you end up p minus 1 minus sigma 3y. We'll get sigma 1 times sigma 2 is minus I sigma 3, phi of x. If you do in the other direction, the only thing which will change, sigma 1 will be replaced by sigma 2 and sigma 2 by sigma 1. That means you change the order of the product, but we know anti-commutation relation tells you changing the order changes sign. So now you get with the I with the plus. Now when we subtract them, you'll get the same expression. So you'll get twice. The quarter will become now a half, and you'll get exactly the representation of the rotation, which was I times 2, bring it inside, the minus is left outside, and the representation pi L of R3. So the same formula as we had it in the regular representation. So the same commutation relations hold also here. So we got a representation of the Lorentz group. It acts not on the space M, on the complexified space M. That means you will have to get a little bit of meaning for this complexification. And I'll give you the clue that I have is really because in reality, for even considering particles, you don't have to describe only their position. They all of them have a rotation frequency, an axis of rotation, what is called the spin. There's no particles which are not spinning, and that's strange. But as you see, under this representation, each object comes accompanied with some kind of spin, intrinsic spin. Let's see how we'll get, not the generators, the action of the group, the boost and rotation and pi L. We will do only about the x direction, which we have to. So to do this, we have to take the exponent. When you have the generators to go to the group, you take the exponent. Now, you see right away how easy it is to work with Pauli matrices. To do the exponent, you have to take the power series of the exponent. And you using the sigma square is the identity. So you'll have the odd powers will give you from the exponent, the odd power will give us the sinh, and the even powers will give the cos of the half angle, omega over 2. If you remember, this matrix we had today in the exercises, that's exactly the boost matrix for the symmetric velocity. Now, for the rotation, you'll get a rotation matrix. But remember, we are now like in the time and space. For instance, rotation about the x-axis, so we are talking about the x-axis. And the generator is I times x1. It means the I is really telling you some kind rotation, but in the plane time and the direction of rotation. That gives you a little bit of clue what the meaning of this complexification is. But would like if somebody will help me to clarify it, they still get a little better clarity of this, probably will reveal another symmetry that we have in the nature, which causes these rotations for all the things. Now it's not so complicated. Do directly now, do the phi of x and phi minus 1, you'll get how the 4-dimensional matrix on the vector x. Look what it acts for a boost. You have a boost, but for the symmetric velocity. But it comes with a boost in the plane xy, but with the I. That means the same way as hyperbolic angles go to regular angles by multiplication by I. Also here somehow we move in the complex part of this space, and we have such a decomposition. For rotations about the x-axis, you'll have rotation about this x1 axis is a rotation in the plane yz, a regular rotation, once more by a half angle. And you'll have also a rotation in the time and x1, which is the axis of rotation, but the axis you change from being real to imaginary, to I times. So this gives a little bit understanding what is this representation and the meaning of the complexification, but still we have to understand till then. Now, it will get a spin hat representation of the Lorentz group on the complexified Minkowski space. What was a big surprise? That this angle, zeta, which is a combination of the theta and phi. Why I put the I on phi? Because phi is periodic with 2 pi. It's like e in power I. Phi is getting continuous. And this angle is invariant under the representation pi L. That means if our observers will be transformed from one to the other by the Lorentz group represented by pi L, then all of them will measure the same angle. Very important observation. And the proof is one-line proof. The original proofs were very complicated until we got there. By the way, historically, similar thing was obtained by Whittaker in 1904. They found 2 functions that with them he can describe any electromagnetic field. And he was able to find them and was very excited. That means the electromagnetic field has only 2 degrees of freedom. And then he gave up. Why he gave up? He didn't find the Lorentz invariance of it. So he said any thing which is not Lorentz invariance is depending on the coordinates. It's not physical. And here how we prove that this is physical. It is invariant. So we have to return to our bipolar coordinates and see how they look in the matrix representation. Remember here we had x0 plus x1. Cos plus sinh gives you e in power theta. The difference here, this place, gives you e in power minus theta. And here you get cosine plus I sine phi, which gives e in power I phi. And here e in power minus I phi. Now you remember this vector is a null vector. That means the determinant of this matrix is 0. It's a simple calculation. It is 0. What does it mean? That the columns are linearly dependent. Let's find what are the column dependence. Column 1 is equal column 2 multiplied by e in power zeta. If you multiply e in power I phi by e in power theta minus I phi, the I phi cancels and you get e in power theta. The second round, you multiply e in power theta minus I phi, theta will cancel, and you get minus I phi. Now, the pi L act on this multiplying from left. Multiplication from left of a matrix acts as a linear map on each column. A linear map preserves the ratio between 2 vectors. That means after applying the representation pi, you still have the first column will be e in power zeta times the second column. It means e in power zeta is preserved. And that zeta is invariant under the Lorentz group representation pi L. So we had some kind of invariant. Now, from this invariant, will be able to describe the field. By the way, it's an invariant and measurable. It uses only what? The direction. The direction is the easiest thing to measure. We define now a pre-potential of a single source field. How we define it? We are using more connected with the electric field. This gives us the motivation, but I think eventually we'll be able to use the whole model also for the for the gravitational. We have seen the acceleration, which is the same as the force, is a rank 2 antisymmetric tensor, F mu nu, and it has 6 parameters, 3 components of the electric field and 3 components of the magnetic field. Is this the most compact description? No. In electromagnetism, they use the 4 potential. 4 potential is a function, co-vector valued function on space-time, and the connection to the field is differentiation. As the potential, the regular and classical mechanics was a function, and differentiation give us the force. Now also, since the force is a rank 2, so the pre-potential has to be rank 1, and it is a vector. So get a 4 vector, and this is the derivative. So this description is more compact. It has only 4 variables. Even those 4 variables, since differentiation, such differentiation, a lot of things became 0. So you can put extra condition and restriction, which is called gauge condition, and you can reduce it really to 3 parameters. The question is, can you get even something better? And that was Whittaker's attempt to get, and he found that 2 functions are enough. He didn't saw that they are connected to 1 function, complex valued, but the question is here, does there exist a function of x on space-time that A will be the gradient, negative the gradient? No, that cannot help. Why? Because you take a gradient and then you have another differentiation. Twice differentiation gives always 0. So you must, to get like a Laplacian, you must put inside some operator, which is not a differentiation, which will change to have 2 consecutive differentiations. And when you use complex cases, complex numbers, you use some kind of conjugation. You need to introduce after the first differentiation a conjugation, and then you'll use it as a 4 potential, and then you'll obtain the field. So we are looking now at conjugation on the space-time, and since we want to use our representation pi L, we want that this conjugation will commute with pi L. And here is the easiest conjugation that we can introduce. It will multiply phi of x from the right now. If you have a multiplication from right and left, the 2 multiplications commute because of associativity. We can multiply first by left and then by right, or first by right and then by left. It's exactly the associative law. And we have seen the exercise of tensor that the product is associative. So it is a symmetry because sigma square is the identity. Applying twice will give it identity. What it is doing in the representation phi of x is very simple. It changes the sign of the second column. That's all. Very simple representation. And then we define the prepotential to be k times zeta of x. K is the strength of the source. For sure, the potential as the source is stronger, you need the field will be proportional to the strength. And this will be the angle. If we don't want to have the discontinuity at 0 And 2 pi for phi, we can take the exponent, e power zeta x, we will get a continuous function. The two representations occur in physics. In electromagnetism, they like to use the psi, this one. In quantum, they use this one. And really, you can do, those are equivalent. Only interpretation, how you interpret. In quantum, they want to have it as action on functions. So the continuous description is better. But all the calculations are the same. Now what we'll do the next time, I will show you the following. If you calculate the gradient of this psi and take the conjugation, we'll get a 4 potential. In what sense? The real part of it is the famous 4 potential for electromagnetic field generated by a single source. It was done by Leonard Vickers potential, which is the basic potential for all electromagnetism. All the radiation and all those things follow as a result of this Leonard Vickers potential. It occurs, the real part of this complex potential. This complex potential has an additional symmetry. The complex part is in order to preserve the symmetry, which is some kind of helicity preservation, which is also an additional property. But this, to do this, we'll have to work out a whole machinery, how you work effectively with these bipolar coordinates that you've seen. They are very natural coordinates, fitted for the whole problem, considering field propagating with the speed of light. And we'll have to develop this machinery. And I hope after the next lecture, you'll have enough tools to do research, continuing this research. By the way, we got something very surprising. Psi of x, what it is, why I denoted psi of x. It is the same term that physicists were using in quantum mechanics to describe particles. They use complex valued functions on the space-time. Psi of x is this one. They also figured out that the representation of these functions is spin half. And we got it also automatically. We got even covariance under the representation. So it is really getting us both to electromagnetism and both to quantum models. And better understanding them, that will give us better understanding of the whole relativity and quantum. Mention a few open problems, that everything that we discussed today. It's not homework because probably it will take more than 1 week to solve them. You have to find the meaning of the complexified Minkowski space. How is this relation of the 4-dimensional complex spin domain? I'm sure that really, as a domain, we are talking about the complex spin domain of dimension 4. It is the right dimension, etc. But we have to see how using, for instance, the natural basis that we have there, not as matrices, but using quadrangles, may even simplify a few things and giving meaning. For symmetric velocities, we have seen on the exercise that then the vector field became complex analytic. Do we have this complex analyticity here on this MC with the representation pi L? That would be very interesting. That if we could get complex analytic domains and having for all those things the physical interpretation. Another thing is a very important problem, and it has very important implications for gravitation. One of the things they understood, they have coordinates close to our bipolar coordinates. Not exactly, but close. And they want, very important for them is to find the connection of gravity and quantum. And some leaders in this area formulated really is to find how all general relativity is only invariant under the Lorentz group, but not under the Poincaré group. And without bringing in the Poincaré group, you cannot reach to quantum. You have to have also translations. And it is not so easy when you have talking about curved space-time, even if the curvature is small, even approximately. There's a lot of problems. So I hope here it will be easier to get the Poincaré group under those representations. Another thing, this is probably an easy problem, how pi L can be represented by bipolar coordinates. Maybe this is an exercise. Okay, that's for today. And hopefully we'll be able to, next time we'll get you more techniques to be more mathematical, because we have to develop a new machinery, how we work in this basis effectively. And that's what we'll do the next time. Okay. It was nice to meet you, and see you the next week.
Thank you.
Bye-bye.